So to start today, I'm going to ask you to think back to the lecture videos on electrostatics and on magnetostatics. And what we saw in those is that a static, or by static we mean unchanging or a constantly valued electric field, it's produced by any stationary charged particle like an electron or a proton. And we used Coulomb's law to determine the E field due to a stationary charged particle. Similarly, in magnetostatics, we've learned that a static magnetic field will be produced whenever a DC current flows in a wire, and we quantified the amplitude of the magnetic field by using the Biot-Savart law. So we had two laws, one that the Coulomb's law that told us how strong an electric field is due to a stationary particle, and the Biot-Savart law that told us how strong the magnetic field is due to a constant DC current. Well, now what I need you to think of is we're going to change the situation, and instead of a static magnetic field as we produced by a DC current, or maybe with using a magnet, let's say we change the amplitude of the field somehow. We make a dynamic field, and by dynamic I mean that if we measure the field strength at one point in place in space, the field strength is going to change. So how would we do this? Well, an easy way to do this is just move a magnet around in space, physically move it around. The magnetic field at any point in space would then change as the magnet moves around it. For example, if we spun a magnet in a circle around its central axis, we would create what we would call a dynamic or a time-variant magnetic field. And it turns out that a time-variant magnetic field will always produce a time-variant electric field. And it is also true that when we produce when we have a time-variant magnetic field, that the electric field that it produces is time-variant. I may have just said that twice, I'm not sure. The point is that if we move a magnetic field in space, if we change it in space, it will always produce a time-variant magnetic field. So if we have a dH dt, and what I'm saying there is I've just got some time variant magnetic field. It's not changing, or it is changing. The rate of change is not zero. That produces a electric field that is also time variant. So what that is saying is we can cause an electric field to exist by two different phenomena. One, we can just have the presence of a charge. If we have a charged particle sitting there, it creates an E field. Whether the charged particle is sitting there or whether it's moving, it creates an E field. If it's sitting there, it's a static E field. If it's moving, it's a dynamic E field or a time-varying E field. The second way we can create an electric field is by having a time-variant magnetic field here. So in classical E&M, this is described by a law called Faraday's law, which states that any change in the magnetic environment of a coil of wire will cause a voltage to be induced in the coil. No matter how the change is produced, the voltage will be generated. The change could be produced by changing the magnetic field strength, by moving a magnet towards or away from the coil, moving the coil into or out of the magnetic field, rotating the coils relative to the magnet, etc. Similarly, what would happen if we decided that we wanted to change the electric field strength as a function of time, meaning that we've changed the amplitude of this field somehow such that the field strength changes? An easy way to do this would be to hook up a capacitor to some sort of function generator. It could be a sine wave function, it could be a square wave function, or anything like that. Well, then the E field in between the plates of the capacitor is going to change as a function of time. Again, we're saying that the derivative of the function isn't zero. So, well, what happens then if we create this time-variant electric field? Well, it turns out that if I have a time-variant electric field, I create a time-variant magnetic field. So this opposite relationship is true. And this kind of makes sense since we already knew a DC current for magnetostatics creates a static magnetic field. So it's pretty natural that an AC current would create a time-variant magnetic field. And In classical E&M, this is described as Ampere's law, which states that the magnetic field in space around an electric current is proportional to the electric current which serves as its source. So just like in magnetostatics, we had a constant or a static magnetic field due to a DC current. It's also true that if we have a time-varying electric field, we'll produce this time-variant magnetic field. So this is interesting. This is a really interesting result, because if we take an E field and we make it time variant, meaning we change its value as a function of time. For example, we would drive an antenna with a sinusoidal voltage and current signal. What that does is it creates this time variant magnetic field. Well, we already said that a time variant magnetic field creates a time variant electric field. Uh-oh, we're in a closed loop. And that's exactly what happens with electromagnetics. It's a really, really interesting result. All we have to do is create a time variant magnetic field. That will, through Ampere's law, create a time variant magnetic field. That time variant magnetic field, in turn, through Faraday's law, creates a time variant electric field, which through Ampere's law creates a time variant magnetic field, right? You kind of see what's happening here. And so this phenomenon of, I'm labeling it H here. We haven't really talked about, or sorry, we have talked about H. So we've got some sort of time variant magnetic field. It causes a time variant electric field, causes a time variant magnetic field, and we get this like what we call cross-linking of E fields and H fields, and this is called a self-propagating E&M field. This is really what we're talking about when we say that E&M fields radiate. Radiate just means that they're self-propagating cross-linking fields. So for example, say we have some sort of time-varying current, in this case indicating that this is called J. It's some current antenna, some current on an antenna. I use J because that's actually current density. It's amps per meter, not amps. But say we've got some sort of current density, amps per meter, meter squared, excuse me, amps per meter squared. And let's say it's sinusoidal. J is a sinusoidal current. This time-varying current is going to produce a time-variant magnetic field, H. Through Faraday's law, time-varying electric field is generated, which through Ampere's law generates a magnetic field, and so on and so forth. So this cross-linked electric and magnetic field will propagate away from the antenna in all directions, and we call this radiation. It's a really interesting phenomenon.